Tracing is awesome if you know how to use it. Fellow members of the Ceph community, thank you for attending my talk about tracing and Ceph. My name is Mohamad. I'm a software engineer at SUSE, and I work in the Montreal area up in Canada. This is the outline for my demo, pretty simple. There's this idea that has been thrown around on the Ceph dev mailing list and between the developers to change the backend of the buffer list data structure in Ceph. So this is what I'm going to be mostly talking about during this talk, how we can use tracing to do an analysis that allows us to take such a decision. I will then sneak in a small comment or a small analysis about logging in general in Ceph. And finally, I'm going to do a small tracing demo, which I have already pre-recorded, just in case. So we have this hypothesis that changing the backend of buffer list might make an improvement for performance. Buffer list is simply a class that chains buffers together. It's a list of buffers. And it's currently implemented using a linked list from the standard library, which is just a bunch of nodes that are referenced by pointers. They're not contiguous in memory. Some people have suggested that we move to a vector, which has all the elements of the buffer list would be contiguous in memory, because the myth is that a linked list is usually more efficient, but because of CPU caches and because of locality, that might not really be the case. How do we measure a gain, if any? I mean, such a change might be really, really small and insignificant. Doing a Rados bench or running FIO might not really expose the benefit or the regression, or it might be covered by something else. As important as buffer list is, a lot more goes into a workload in Ceph. I think we can use tracing for that. Ceph currently supports trace points, LTTNG trace points. You can define a new trace point that way. Here I have define the trace point that is called buffer list push front. Quite easy. This is the current implementation of the push front method of buffer list. It simply calls an insert on the standard library container that is used. I have instrumented the code as such. Just call the trace point before and after the insert, and we'll see what happens between these two trace points. The cool thing about LTTNG is that it allows you to add context to a trace point. So every time you have an event that is recorded at runtime, you can let that event or that trace point hold extra information about the context of your system. Here in this analysis, I have added cache misses, L1 data cache load misses, TLB misses. So TLB is simply a cache structure for resolving memory addresses from virtual memory to physical memory, which might be very expensive if you're doing low-level profiling. On x86, 64, it ends up in 4 additional access to memory for 1 TLB miss. I'm also looking at the number of instructions that it takes to do a push front or a push back. The number of instructions in itself is not really relevant. It's not really important because this can change from a compiler version to another. What's interesting is that it lets us guess which code path is taken at runtime. The approach I took for measuring the impact of changing buffer list from a list to a vector is the following. I have a micro benchmark that creates 1,000 buffer lists, and in each buffer list, I append 1,000 buffers to it. So we have 1,000 buffer lists. Each buffer list has 1,000 buffer. I have an L1 cache size of 32K and an L2 cache of 256. And during the micro benchmark, I like to disable C states, Intel Turbo Boost, hyperthreading, and whatever might come in and interfere with the frequency of the CPU. When you're done, this is what you get. You get hundreds of thousands of these lines, which don't look really interesting, and they look pretty boring, to be honest. But if we dissect one, we see that it's actually pretty easy. You have an event. Each event has a timestamp. You have the CPU ID in which that event was recorded. And then you have your context, the number of cache misses, instructions, L1, data cache load misses, and TLB misses. And you have your payload, which I have defined. 0 is I'm going into the push front, and 1 is I'm going out of it. So you can guess if we do a difference between these values for 2 consecutive trace points, we know what happened between 2 trace points, between 2 consecutive ones on the same CPU. This is the average latency of pushback for different data structures. Vector is in red, list is in green, double-ended queue is in purple. But averages aren't really interesting. Instead, let's look at individual pushbacks. For all of these graphs, the y-axis is always the latency, so it's really how much time it takes to do one pushback. The x-axis is, on the upper left, the number of instructions. Upper right, L1 cache misses, which is what we're interested in. Bottom left is number of TLB load misses, and bottom right is the number of cache misses, so all levels of cache. Let's focus on the upper two, the number of instructions and the number of L1 misses. If we look at the number of instructions for a list, all of the green dots, they have the exact same number of instructions every time. Because a list is always the same way. You create a node, then you update a reference to it. And it really is the exact same number. It's really interesting because I at least always had the impression that I can't really see what's happening in the CPU because it's so obscure and there's so many runtime optimizations. But the number of instructions, you can actually predict how much the next function, how many instructions it will take. For the green dots, as I said, there's only one code path that is taken. For the purple one, there are 2, which means that a pushback using a double-ended queue either takes 3,000 instructions or it takes 4,000 instructions, with the focus being on the 3,000 instructions, which is the fast path, meaning there's enough space in the current memory block to append a new buffer. And sometimes, when there isn't, then a slow path has to be taken, which is the 4,000 instructions path. For the vector implementation, you have many code paths that are taken. You have one that is prominent, a little over 2,000 instructions, which is, again, the fast path, meaning there's enough memory, there's enough space to add a new element. But you have many other instructions, many other code paths that might be taken. At first, I wondered, how is that possible? I know that there are only 2 code paths possible, either the fast path or the slow path. But if you think about it, you have to move elements when you're crossing boundaries. And the more you have elements, the more instructions have to be executed. So it's pretty straightforward. And you can confirm that by looking at the number of branch misses. So you have either 0 branch misses or you have 1. You have 0 branch misses when the CPU, when you have enough memory to append a new element, which is what the CPU expects because it's the hot path. But sometimes you have 1 branch miss when there isn't enough memory left. The upper right graph is the number of L1 misses. And again, we want to be to the left and down. Left meaning we want few cache misses, and down we want low latency. And we have pretty much that for everyone, but for the list, for the green dots, we have plenty of outliers with more L1 misses. The number of TLB misses doesn't really seem to impact much. I mean, the more you have TLB misses, the higher your lower bound will be, but it's not really significant, so we'll just ignore it for now. The next step was to make the buffer size vary. So I'm still appending 1,000 buffers to a buffer list, but I'm making that buffer size larger. And let's see what happens as I increase it. as soon as the buffer size grows to the same value as my L1 cache line, I start having a lot of L1 cache misses for the vector, which means that it is cache friendly, but it's less cache friendly it becomes less cache friendly as the buffer size increases. Double-ended queue seems to do just fine. If I do the same experiments for the toString toStr function, which is an access function, it's not an append, it's an access function. Again, we see there isn't much difference between the three data structures. Again, the list seems to be less cache efficient, as we see here. But I don't think it's a drastic change on average. It's quite interesting, though, to see that double-ended queue seems to really outperform the other two data structure. If you look at push front, for those who know the vector implementation, it's very efficient to push at the end, but if you want to push at the beginning, you have to shift all the elements. And this is what you get for a push front. The vector just becomes awful, which is understandable because you always need to shift all the elements every time you do a push front. You have all values of possible instructions because you always need to shift all the elements. The number of it is still somewhat L1 cache friendly until this point. But although it's a little bit L1 cache friendly, it's still high latency. So it's really an awful backend to use if you're doing a lot of push front. Let's see what happens when we increase the number of the buffer size. It just worse and worse. Double-ended queue again is pretty good. What else can we look at? I showed only 4 PMUs, for performance monitoring units. There are many more that you can look at. A cool one is looking at the CPU cycles, because if you have the instructions and you have the CPU cycles, you can calculate the IPC, and you want that to be close to 1. You can look at branch prediction methods, which I've already talked about, page faults. And the micro benchmark, page faults aren't really interesting because nothing really happens. The next step would be really to implement, to be able to really run Ceph itself with different backends for buffer list. What I did for these was take code from Adam Emerson's repo and Jesse Williamson's repo, which they have started to do. So Ceph crashes if you start Ceph, but you can run the unit tests, and this is what I used for this experiment. So from these runs, double-ended queue seems to really work best, but to really get to a conclusion, we need to see how real Ceph uses buffer list. A small word on logging. Currently, this is how we do logging in Ceph. We use the dout function. We give it a severity and a string, and you get logs. And there was also talk to make this a little bit more efficient. So what I did was change this for a trace point at LTTNG. And by doing that, we take off all the locking because LTTNG is a lockless tracer. It uses per CPU buffers, so there's no locking. And it's pretty efficient. And I didn't see any difference. I didn't see any difference between dout or logging in Ceph, which uses locking, and I think it uses a linked list to keep track of logs and then flushes them at a later time. I didn't see any improvements, which means that the bottleneck of this is string manipulation. This is just what I think it is. I wasn't able to really dig a lot further than that, but from early results, this is what it looks like. Finally, I'm going to do a small demo using Trace Compass, which is a trace viewer for LTTNG and a bunch of tracers. You do not have to instrument your application to use Trace Compass. You can just take a binary and run it and see what happens. You can instrument functions if you want, and all you need to do for that is recompile your code with GCC's instrument function flag, which Ceph supports. So for this next demo, I have recompiled Ceph with basically GCC's flag and nothing else, and I just trace the kernel and the function entry and exits. By the way, the following demo also works with traces from ftrace, kernel traces from ftrace. So if you don't want to use LTTNG, that's fine too. This is Trace Compass. You have 3 views. The upper one is the control flow view. It shows the state of all of your processes on the system through time. The green is running in user space. Yellow is blocked. Orange is preempted. So you see Swapper is preempted often, which is good because Swapper is the idle task on Linux. So we want it to be preempted whenever we can. It's really a list of all your CPUs. This is a vstart cluster, so you see all the Ceph threads as well. Here I ran a Rados write with a single write. And you see that Rados is created, runs a little bit, then is blocked for the entire time, runs a little bit at the end, and quits, which is expected on the client side, right? This is the duration for which it ran. If we zoom in, we can see more granular states, such as system calls. All the blue states or system calls, you can even see which system call is called. This is the exec v system call. So it really gives you an insight on what your process is doing, and it's great for reverse engineering, and if you want to understand what's happening. Here, for instance, there's the open system call, which Rados does. And you see it doesn't open on the log file, .log, so it's for logging, basically. It does another open. It does an open, a write, and a close, back to back. So we can kind of guess what's happening here. And if we look at the open system call, it's opening the /self proc self task com, which is the name of the process. It does the open system call. It gets a file descriptor in return, number 8. It then does a write on FD number 8, and then closes file descriptor 8. This might not be Rados itself. It might be exec that does that for Rados. Now, as I said, the Rados process runs a little bit at the end, waits, and runs a little bit at the end before quitting. And I want to know what happens, why is it blocked, what is it blocked on, and what's happening on my system. So all I have to do is open this other view called the critical path view or critical flow view right here, and I tell it to analyze the process, and it gives you the critical path of Rados, and you see what it's waiting on. And this is all using kernel trace points, so things like try to wake up and timer events, IRQ events, scheduling events, etc. And you see what's happening. So you have a bunch of K worker threads that are involved. And I'm going to zoom in now in a second on this, and you'll see that it's not super efficient. there might be something to be done here. On your critical path, the critical path of the Rados client goes through all of these key worker threads, and the orange is the blocked or preempted state. In other terms, it's the time between when the process is created and when it's scheduled on CPU. And you see it's greater than the amount of time it actually runs. So there's a lot of wasted time here. We might be able to get away without creating all of these key worker threads. I haven't done a lot of analysis on this, so I can't really explain it at this point. But the key worker thread or kernel worker often used for I/O, I think. You also see communication between TP, OSD, TP, which was part of the OSD. The purple states are the blocking I/O, and this is expected here because the write does obviously synchronous I/O. Finally, you have the bottom view, which is the call stack view. And if you do the CMake with the extra argument that I showed, you will get this information. You will see which function your OSDs are running at any time. And this is all threads of the OSD. And it's cool, it's really cool, because sometimes you'll see loops repeating based on the colors, and you'll see, sometimes inefficiencies really jump out when you're looking at this, sometimes not. But you really need to know the code and know how things work to really make sense of this. But it can be quite powerful. And obviously all three views are synchronized, so you can see that nothing is happening here for the time it was preempted, which makes sense. And the good thing with LTTNG traces is that there's also a library, libbabeltrace, if you want to do automated analysis. So for instance, we could easily write a script to compute how much time is spent in a specific function or in a specific thread or whatnot. I'm going to cut this short. My presentation is done. Thanks to Jesse Williamson and Adam Emerson for unknowingly providing code for this demo. I also want to thank the Ceph community, which has been really inclusive. And as a developer, you see it even when you're a newcomer and a newbie. You really feel the openness, which has to be mentioned. I think it's really great. It shows. It's clearly an active effort. I also want to thank Leo for his help this week. I have heckled him with my presentation. Any questions?